In the second video about the Nobel Prize in Physics for 1903, we're going to look at the three Nobel Prize lectures of the winners, Henri Bequerel and both Curies. We start with Henri Bequerel, radioactive substances, especially radium. This is of course summarized by me. The actual lecture is longer. If you want to read the complete lecture, you can follow the link at the end of this lecture to the official Nobel site, which I got it also from. Bequerel starts with saying that he can only give the main lines of the history of this subject. The Curies in the lecture will deal with their part. It starts with the experiments of Röntgen and his extraordinary rays. Bequerel starts to say research phosphorescent materials, especially uranium, is because of the exceptional structure indicated by the bands of its spectrum. The uranium in double sulfate of uranium and potassium emitted rays which made photographic plates black. Bequerel discovered that the rays were not related to light, heat or electricity, thus a new phenomenon. The passage of time did not seem to change the intensity of the emission. It remained constant. The radiation was able to discharge electrically charged material located at some distance, making this a second method of studying the materials. The photogrammetric, of course, was the first. All uranium salts, whatever their origin, emit the same kind of radiation. Uranium discharges spontaneously under influence of its own relation in air, but not in a vacuum. It also makes the air of other gases conduct electricity. It ionizes them, you would say now. Rutherford discovered that the conducting processes of the gas through which the radiation of the uranium passes are completely equal to the ionization caused by other factors. A number of other phenomena were observed. For example, phosphorescent calcium sulfate on a glass plate, see figures 3 and 4, were photographed showing reflection and refraction of the rays. But, strangely enough, it could not be reproduced. This and an experiment by Trost and Newman-Gillespie led to believe that this kind of radiation cannot be reflected or refracted at all. In 1898, Schmidt and Madame Curie observed independently that thorium has properties like uranium. These were studied also by Owens and Rutherford. Rutherford also Nobel Prize winner a little later. You see the four figures related to, you see they are not of very good quality. If you want to look at them better, maybe you should visit the official website. Madame Curie measured the ionization of air and concluded that some minerals are more active than metallic uranium. Thus, a substance more active than radioactive, that is, than uranium must be present in those minerals. The Curies used Joachim Stahl pitchblende, separated it from bismuth to get the new element they called polonium. From active barium minerals, they isolated another new element they called radium. Radium is more than 1,000,000 times more radioactive than uranium. The intense radiation of radium excites the phosphorescence of different materials and restores the ability of crystals to phosphorescence under heat. Radium salts can also become luminous spontaneously under influence of their own radiation. The Curie sent me some radium. Its radiation differs from that of radium. See figure 5, that must be wrong. That must be polonium. Yeah, so its radiation from radium differs from that of polonium. See figure 5, an experiment in which radium rays pass through materials and polonium rays do not. Giesel and Meyerheim von Schweider discovered the rays can be deflected by a magnetic field. Bequerel also experimented with radiation passing through magnetic fields, for instance, see figures 6 and 7. He noticed that the rays emitted by polonium were not deflected and that there are two kinds of rays, one that is highly deflected by a magnetic field and one that is not. The Curies observed that both kinds of rays were present in rays coming from uranium. Rays coming, and they are now called alpha and beta rays, from polonium are increasingly absorbed when passing through thicker materials, see figure 8. For the other rays, now called gamma rays, the inverse is true. Villard found that gamma rays behave much like X-rays, Röntgen rays, while beta rays behave like cathode rays, we now call them electrons, have mass and a negative charge. If they are traveling normal through a magnetic field, the trajectory becomes a circle in the field. If the angle is different, it becomes a helix. A beam of alpha rays are dispersed by a magnetic field as light is by a prism. Alpha rays are positively charged and heavier than beta rays. Now we know they are helium nucleuses, but that wasn't known all that. Bequerel describes several further experiments, which I have skipped here, with the gamma rays, and also see figures 9 to 11. Yeah, it is pointed again and again to these figures, but it's hard to see anything, in my opinion. But for beta rays, the RH value is equal to mv divided by E, and for alpha rays it is between 600 and 2500. Now, what is the RH value? R is the radius of the trajectory in the magnetic field. The beta particle follows. H is the strength of the material field. Those two multiplied is the RH value, and that's equal to mv divided by E. What is m? M is the mass of the beta particle, v is its velocity, and E is its electrical charge. Furthermore, general experiments. Place the active material in a deep, narrow groove in lead, producing a thin beam. Place it parallel to a uniform magnetic field. A photovoltaic plate is placed at a right angle to the beam, and the light is reflected by the pole is eliminated by a minimum coil. See figures 12 to 15. The alpha rays are also shielded out. So the gamma rays are not seen on the plate since they are not deflected. Only beta rays remain. Also, secondary rays are photographed. These are generated by primary rays interacting with the surface. These better behave like cathode rays, which were discovered earlier, in a magnetic field. We now know these are electrons. Madame Curie proved that the charge is negative, while the remaining source becomes positive. So, electrons are taken away from an atom, leaving a positive ion behind. Okay, Bequerel showed that beta rays are deflected by an electrostatic field. Dus not only by a magnetic field, but also by an electric field. The trajectory in such a field is a parabola with parameter m divided by E. That's again the mass divided by the charge. And also v squared by F, which v is the velocity and F is the strength of the electrostatic field. See also figures 15 and 17. Kaufman's more precise experiments determined that the speed of the beta rays was also that of the speed of light. Abrams' concept suggests that the mass of the electron is mostly part of electromagnetic reactions. Well, that was later superseded by Einstein's theory. But anyway, alpha rays was first observed by Bequerel coming from polonium. Rutherford discovered that alpha rays can be deflected by a magnetic field in the opposite direction compared to beta rays, and alpha rays appear to be identical to Goldstein's kanaalstralen, which were discovered earlier. Bequerel photographed alpha rays trajectories, see figure 18, in a magnetic field, and he determined that the mass of the beta rays is more than 1,000 times that of alpha rays. This must be reversed. So now it's right. Beta ray particles are 1,000 times lighter than alpha particles. Alpha rays are very absorbable, most active part in ionizing air in which it travels. The third kind of rays, gamma rays, have a great penetrability and non-deflectability in a magnetic field. So it is not deflected in a magnetic field. See figure 19. The intensity of gamma rays can therefore not be measured by ionization of air or by a photographic plate, since they easily pass through. The secondary rays are more absorbable. Secondary rays are when primary rays hit the surface, secondary rays are produced. They are more absorbable and can darken a photographic plate, so they can be easily investigated. Falling rays on a glass plate produce secondary rays, as I said. See also figure 20. Uranium and polonium transmit gamma rays. Radiation can cause chemical reactions in a photographic plate, change the color of glass, and alkyl sands, paraffin, celluloid, paper, etc. can produce fluorescence, produce ozone from air, ionize all gases and liquids, etc. Marie Curie discovered that radium salts emit heat. She and Dewar made gaseous hydrogen by dropping radium into liquid hydrogen. Radium rays also cause physiological effects in the eye, in the skin, as X-rays also do, Röntgen rays. This causes some damage, implying that these rays may also be a treatment for lupus and for cancer, which turned out to be true. It's still used. Thorium and radium emit energy in a particular form. Energy is released together with an active vapor, which can be isolated using tin foil. The emanations settle on all bodies and making them radioactive. But this activity disappears when the body is no longer influenced of the active source. Rutherford discovered this for thorium and the Curie for radium, and this is called induced activity. The activation does not occur in a vacuum, thus when one removes the gas. Water extracted from an active salt is also active, is radioactive. A gas around radium itself becomes slightly active and emits only low energy rays. Its activity halves every 4 days. Air charged with emanation produce phosphorescence of various objects. The emanation itself behaves much like a glass, as the Curies have shown. Rutherford and Surrey discovered that the emanation condenses at the temperature of liquid air, and Ramsay and Surrey studied the spectrum of the emanations of radium, and its spectrum is equal to that of helium. The question is how helium came into the emanation is not answered yet. Curie and Giesel observed that every inactive substance which is put into solution of an active substance itself becomes active, but loses that activity again. It's also a general that an active substance taken out of solution, the activity diminishes and later increases again. De Bierne found a way to separate active barium from inactive barium due to the difference of solubility, and so he created a barium that was 1,000 more times active than uranium. This is active radium. The described loss of activity may be explained by the substance trapping their emanations. Elster and Giesel have also discovered the atmosphere of air also contains activated substances. To sum up, the radioactivity substances whose nature is now well established are uranium, thorium, radium, and polonium. Actinium can be added, although very little information has yet been published about this last product. See, it's only at the beginning of the radioactivity research. Reservation must be made about various other products contained by Giesel and about the preparation of active bismuth of active tellurium obtained electrolytically by MacCordick. Besides uranium and thorium, only radium has characteristics which enable it to be considered as an element with properties related to but distinct from those of barium. However, it is worth noting that this absence is never found even as a trace element in ordinary barium materials, and that it is only met with in uranium minerals, where it is found with barium. This fact may well have a significance which will become clear to us later. Radioactive substances, especially radium, give off energy in all known forms: heat, light, chemical reactions, electrical charges, and gamma radiation, and they seem to maintain the same state indefinitely, and the source from which they derive the energy they give off escapes us. Among the hypotheses which suggest themselves to fill the gaps left by current experiments, one of the most likely lies in supposing that the emission of energy is the result of a slow modification of the atoms of the radioactive substances. Such a modification, which the methods at our disposal are unable to bring about at the time, could certainly release energy in sufficient large quantities to produce the observed effect without the changes in matter being large enough to be detectable by our methods of investigation. In the scheme, there would still be scope to wonder whether the transformation of the atom comprises a slow, spontaneous evolution, or whether it is the result of absorption of external radiation. And this is now beyond the range of our senses. If such radiation were to exist, one could still picture the radioactive substances forming it without themselves being altered. So far, no experiment has confirmed or invalidated these hypotheses. Again, it's only at the beginning of the research into radioactivity. If you follow the Nobel Prizes, a lot more will follow. And here again, you see the link to the complete lecture. And then we will continue with the Nobel Prize lectures of the Curies. Then we continue with the Nobel Prize lecture of 1903 for physics. After the first one by Bequerel, which was on radioactivity, a new property of matter. The second is by Pierre Curie on radioactive substances, especially radium, which I mistakenly attributed to Bequerel. But this is correct. Again, summarized by me. Let's get started. The properties of the radioactive substances, in particular those of radium, that's the subject. In 1898, we were the only ones, together with Bequerel, interested in radioactivity, and now there's a lot of research. Now it's 1903. Bequerel discovered in 1896, using the special radiation properties of uranium and its compounds. Uranium emits very weak rays which leave an impression on photographic plates. These rays pass through black paper and metals, make air electrically conductive, does not vary with time, and the cause of its production is unknown. Madame Curie and Schmidt showed that thorium possesses the same properties. Madame Curie also showed in 1898 that all of the chemical substances prepared or used in a laboratory, only those containing uranium or thorium, were capable of emitting a substantial amount of the Bequerel rays. We have called substances radioactive. Madame Curie has studied the minerals containing uranium and thorium. These are all radioactive. She found that some were more active than they should be, then made the assumption that it contained an unknown reactive chemical element. We, Madame Curie and I, that's Pierre Curie of course, not me, sought these in uranium ore and in pitch blende. We have found a highly radioactive substance we have called polonium, and then in collaboration with Beaumont, a second which we called radium. De Beerne has separated the third, called actinium. These substances exist in pitch blende only in traces, but we have an enormous radioactivity. After treating an enormous amount of material, we obtained a sufficient quantity of radiphorous barium salt to be able to extract it from radium in the form of a pure salt via fractionation. Radium is in the series of the alkyne earth metals, and its atomic weight is 225, and it has a distinct spectrum. De Massey has found it out. The general reflex of the radiations from radium are intense and varied. Curie gives examples. A radioactive substance as radium constitutes a continuous source of energy. This energy is manifested by the emissions of radium. I, that's Curie of course, and Laborde have shown that radium releases considerable heat. This release seems to be constant after several years. Radioactive substances can emit rays of the three different varieties designated by Rutherford as alpha, beta, and gamma rays. Beta rays, similar to cathode rays, now we know that they are electrons, behave like negative charged projectiles of a mass of 2,000 times smaller than that of an hydrogen atom. Alpha rays, similar to canal rays, behave like projectiles and have a mass. They are more than 10,000 times more heavier and charged with positive electricity, heavier than beta rays, of course. The gamma rays are similar to Roentgen rays. Thus, we know now to light. Radioactive substances also make surrounding air radioactive, and Rutherford assumed by emitting an unstable radioactive gas. The activity of the such gases disappears spontaneously according to exponential law with a time constant which is characteristic for each active substance. Emanations diminish by half for radium in every 4 days, thorium in every 55 seconds, and actinium in every 3 seconds. Solid substances in the presence of radioactive substance become temporarily radioactive themselves is called induced radioactivity, which Madame Curie and I have discovered. The induced radioactivity, like emanations, are equally unstable and are destroyed spontaneously according to exponential laws. According to Ramsay and Soddy, radium is the seed of a continuous and spontaneous production of helium. Alpha rays, we know. The radioactivity of alpha particles. The radioactivity of uranium, thorium, radium, and actinium seems to be invariable. That of polonium diminishes according to the expansion law. It diminishes by half in every 140 days. The consequences of these facts are making themselves felt in all branches of science. The importance of this phenomena for physics is evident. Curie gives as an example the now abandoned electric mass theory, which is skipped here. But if you want to read it, go to the original lecture. You can find the link at the end. The consequence and in the description of the video. The consequences for chemistry are even more important, and this leads up to speak of a source of energy which maintains the radioactive phenomena. At the beginning of our investigations, we stated, Madame Curie and I, that the phenomena could be explained by two distinct and very general hypotheses, which we described by Madame Curie in 1899 and 1900. The first hypothesis supposes that radioactive substances borrow from an external source radiation the energy when they release. The radiation would then be a secondary phenomenon. Rutherford, Cook and McClellan claims this explains part of the extremely weak radiation. The second hypothesis supposes that the radioactive substances draw from themselves the energy which they release. The radioactive substances would be in evolution, transforming in spite of the apparent invariability. The quantity of heat released by radium in several years is enormous if it is compared with the heat released in any chemical reaction. This leads to the supposition that the transformation is more far-reaching than chemical transformations, and the existence of the atom is at stake, and that one is in the presence of a transformation of the elements. The second hypothesis has shown itself to be more fertile and gives an explanation for the spontaneous disappearance of polonium and the production of helium by radium. They're transformed into each other. This theory of the transformations of the elements has been developed by Rutherford and Soddy, who state that there is a continuous and irreversible disintegration of the atoms of the radioactive elements. Products would be the projectile rays and the emanations and the induced radioactivities. The latter will be a new radioactive substances frequently with a rapid evolution and atomic weights lower than that of the original element from which they are derived. This is a veritable theory on the transformation of the elements. Though an unexpected consequence, the radioactive phenomena can be important in geology. It has been found, for example, that radium always accompanies uranium in minerals. That the ratio of radium to uranium is constant in all minerals discovered by Boltwood. It can be imagined that certain elements have been formed on the spot on the surface of the Earth, or that they stem from other elements in a time which may be of the order of magnitude of geological periods, millions of years. Elser and Geitel have shown that the emanations of radium is very widespread in nature and that radioactivity probably plays an important part in meteorology with the ionization of the air provoking the condensation of water vapor. In the biological science, the rays of radium and its emanations produce interesting effects. Radium rays have been used in the treatment of certain diseases like lupus, cancer, and nervous diseases. All no prizes on that too, later. In certain cases, their action may become dangerous. A more prolonged action could lead to paralysis and death. The radium must be transported in a thick box of lead, and it can even be thought that radium could become very dangerous in criminals' hands. Well, all this has indeed become true. Here you see the link to the original lecture of Pierre Curie, which is a bit longer than the summary here, of course. Some pictures here. This may be interesting. This is radioactive decay. Yeah, here we have an atom which splits off another atom, so you can get two daughter atoms, which are both smaller, of course, than the original one. This is about ionization, and here is described how radiation is detected. If you want to read it, this comes from Wikipedia. You can also stop the video, of course. Here you see a simulation of identical atoms undergoing radioactive decay, as you see, starting with either 4 atoms on the left or 4 on the right. And you see that this radioactive has a short half-time because everything disappears quite fast, while this has a longer half-time, as you can see. Yeah. Is it true, anyway? No. No, they have the same. No. And the number of which they start is different. Well, okay, nice. Here you see an alpha particle. As you can see, it contains 2 protons and 2 neutrons. They were not discovered in 1903, so they did not know what this was. Or, as you can see, they are struggling to find out what it is. Here you see a beta particle, which we now know is an electron. We also know now that the neutrons exist and that they can split in a proton and in a neutron and in a neutrino, by the way. And here you see a gamma radiation, which we now know is a form of light, just like Röntgen rays, ultraviolet rays, infrared rays, visible light, radio waves, microwaves, etc., etc., etc. This was all not known at that time, of course. And here you can see the 3 kinds of radiations, how they penetrate. Alpha radiations are very easily stopped by a sheet of paper. For beta particles, you need a steel plate or something like that, or lead. And gamma rays, well, you need very thick concrete or steel to absorb the most of this, as you can see. But always something comes through, as you can also see. Here you can see also this what happens when a parent atom loses an electron. You see, it goes to become another atom. The same for alpha rays and also for neutrons and protons and positrons, which were all not known at the time. Everything will come back in later Nobel Prizes, no doubt. And you see the periodic system with radioactive elements are colored. Well, if you want to study it of one of the others, you can also go to Wikipedia or you can stop the video, of course. This is also nice. This is one of the original drawings and notes made by the Curies. Yeah, here you see more of their work. And then for the third winner, Madame Curie, she did not deliver a Nobel Prize speech. Pierre Curie did. They were both not present during the award-winning ceremony, as far as I know. Pierre Curie delivered a speech a few years later, I believe in 1905, and Marie Curie did not. However, she did have a chance to have a speech in 1911 when she won a second Nobel Prize. Good. Instead of her Nobel Prize speech, I've found an article by Adloff and MacCordick on the dawn of radiochemistry, which deals with the first year in the research. I've summarized it only and only the parts on the notes they wrote. They wrote 3 notes in that year. Well, here the first note, April 12, 1898. It shows that Pierre Curie was known as a scientist, for instance, discovering with Jacques Curie, that's his brother, the piezoelectric effect. And he also investigated where the energy of uranium came from. Madame Curie decided to investigate this also for her thesis, to become a doctor. Uranic rays also make air conduct electricity, they discovered. This effect could also be investigated, and for the first time quantitatively. Pierre Curie invented the prototype reorganization chamber. See the figure? We've already seen it. This is this one. Yeah. Okay. He invented the prototype ionization chamber, which was used for those measurements. The working of the device is explained in the article. I have skipped it. If you want to read it, follow the link in the description of the video. But Arappes was able at first to quantify the emission of uranic rays based on the intensity of the current. The device was not easy to operate, but it was an invaluable tool, also adopted by others in the field and still in use in the early 50s. See for this Marie's notebooks. She started to search for elements and compounds capable of imparting conductivity to air. She borrowed many samples from others. The article lists these samples and the owners, which I have skipped here. But if you want to see them, go to original article. Remarkable, the name of Pierre Curie is not on the paper. Well, except for thorium and uranium, the intensity of the radioactive materials was roughly proportional to the fraction of the elements in the compound. That was already observed by Bequerel. Uranium metal produced the same radiation as uranium salts, but with a higher intensity. This was the start of radioanalytical chemistry. The measurements in the second sample of table 1 were confusing, and it was difficult to understand why black uranium-205 exhibited a 10% higher energy than metallic uranium. This odd behavior appears also still unexplained in Marie Curie's thesis and has been properly clarified by R.L. Wolke, Madame Curie herself, and Schmid. They emphasized that all active minerals contained uranium or thorium. Pitchblende and chocolate are 4 and 2 times more active than metallic uranium, which was less active than the materials used before. She concluded that an unknown element must exist in those materials to explain the stronger radioactivity. The same is true for autunite. Interestingly enough, the sample investigated included 2 potassium compounds with feeble activities. The article then discusses the other active elements were existing in the materials, but were not yet discovered. Probably the emitted radiation was too low to be detected. Pierre Curie abandoned his own research to join his wife to find the predicted new element. Marie Curie reported the discovery of thorium, but Schmid had discovered it just earlier. But more was to follow. July 1898. The second note was signed by both Curies and announced an element more active than uranium. Also, the word radioactive was used for the first time. The note was presented at the Academy by Henri Bequerel. The analysis of pitchblende followed the scheme of Fresenius and had been done before. The Curies adapted it to measure the radioactivity of all compounds that were isolated. The fraction that was still left becomes intrinsically radioactive. Was more than 2.5 times more active than uranium. The flowchart in figure shows that the producers described in the publication. And maybe these are the flowcharts. What she did, starting with pitchblende and separating all its constituents. I find where I was. Yeah. The article gives some details on the procedures they used. I skipped them, but if you want to read them, go to the article itself. The treatment of the acidic solution with H2S was already a significant step, since sulfides were more active than that of the residual solution. The latter contained uranium and thorium. After several other steps, bismuth remained. The separation of the active substance from bismuth by wet method was found to be difficult. Marie Curie precipitated sulfides from a nitric acid solution containing lead, bismuth, and the active substance. Noteworthy, the research on reactivity now turned from physics to chemistry. The Curies were not chemists and they had to ask for an assistant, BMO. The solid was 150 times more active than uranium, and Pierre Curie heated it at several hundred degrees, causing further separation, and a sample 330 times more active than uranium, and after repeating 400 times. They discovered an unknown metal, similar to bismuth in its analytical properties, to be named polonium. Announcing the existence of a new invisible, only identified solely by its emissions was unique. Measurements by Demarquet did not confirm the discovery, so little polonium could be made that it could not be seen and could not be analyzed by spectroscope, which was a disadvantage, of course. Madame Curie and de Berne started with tons of the residue from the sulfuric acid extraction of uranium ore, and their product weighed about 2 milligrams and probably contained about 0.1 milligrams polonium. That's something, starting with thousands of thousands of kilos. The Curies noticed with astonishment and great perplexity that polonium was progressively disappearing. Moreover, they could not imagine that they were dealing with tracer amounts of the new element. Without knowing it, the Curies had invented the use of carriers. In the final step, the polonium was effectively carried by bismuth. The assignment of polonium in the periodic table of the elements does not seem to have preoccupied the discoverers. The article does, which is skipped here. So, but again, if you want to read it, go to the article itself. The Curies were on the verge of more important discoveries. Madame Curie conserved a sentiment of ownership for polonium, which she defended hard. In one sense, she was right, owing to the role of her polonium in the discoveries of the atomic nucleus, the neutron, artificial radioactivity, and fission. Then the third note, December 26, Christmas Day, 1898. Polonium was discovered first, but it was soon followed by a new element. The Curies worked hard again with pitchblende residue. They focused their attention on the remaining sulfides, this time barium sulfide instead of bismuth sulfide. The spectra of the barium sulfide showed that something else must be there. Three arguments. Normal barium is not radioactive. The increased radiation of barium chloride, which was separated by crystallization. And most important, the MacCordick spectral test was successful this time. De Massey found lines which cannot be linked to known elements. The Curie proposed the name radium for the new element, which also belonged to the alkyne earths. Another proof would be to determine the atomic mass. Madame Curie was obsessed by this for years, and she published the value of 225 plus or minus 1. You can here see the present-day value. In 1901, she published it. Radium could be definitely placed in the 88 EKB position in the periodic table, dus op place 88. The authors now compared the radioactivity of the four known radio elements, dus uranium, thorium, polonium, and radium. The last two left an image on the photographic plate within half a minute, and uranium and thorium only after exposures times of several hours. The Curies ran out of material and they needed more, and recovered 100 kilograms from M2S, which helped a lot. The Nobel Prize for Physics was attributed in 1903 to Bequerel and the Curies for their joint researches on radiation phenomena. At this time, no mention was made of the discoveries of polonium and radium, and Madame Curie got the second Nobel Prize for that in 1911 for chemistry. Then the epilogue of the article. The discovery of polonium and radium stimulated new interest in radioactivity. Else, Geisel, Meyer, Suez, Rutherford, List, Geisel, De Haan, and others also started to investigate. The Curies had begun the extraction of radium from several tons of residue from ores. A.D. Pierre took over the proceedings of the pitchblende residues, and he announced new fractions which had properties of titanium with 100,000 times higher radioactivity than that of uranium, but it was false. The substance was a mixture of two thorium isotopes with little, if any, of the element now known as actinium, which was already discovered. The real discoverer of actinium was probably Geisel. Madame Curie was aware of the importance of proving that radium and polonium were elements. She recognized that it would be much easier for R.W. Marquardt claimed the discovery of the new radio elements in the bismuth fraction radiotellurium. A harsh controversy first. For her, radiotellurium was identical with polonium. Neither of the authors was in the end completely right. The chemical properties of polonium were undoubtedly those of the radiotellurium. On the other hand, studies showed that Marquardt's statement on the constancy of his activity of his radiotellurium seems to be irreconcilable with what we know about rays. He reported in January 1905 that radiotellurium decayed within a half-life of 190.8 days. 1 year later, Marie Curie announced that she found a half-life of 140 days for polonium, proving the two were identical. Marquardt remained unconvinced that the original polonium of the Curies was not a mixture of several radio elements. Madame Curie was still reluctant to agree with Marquardt that polonium was a monologue of tellurium. To know its properties, polonium should be available in weighable amounts, and that took 5 more years of work to achieve, which is not part of the article. As said, the complete article can be found following the link, which you also find in the description of the video. Thank you for watching, and maybe till another time.